Newbill for the EE599 project number 3 assignment. Today I will be talking about Sprint, a scalable chiplet-based architecture for CNN inference. To start, we'll talk about the knowledge gap and the motivations for this paper. Prior works focused on monolithic CNN accelerators. These focused on improving data reuse and assumed uniform latency. However, increasing CNN model size required scale-up systems, namely chiplet architecture. Furthermore, very few prior work explored implementing chiplet-based architectures for machine learning in this way. Second, we have electrical mesh interchiplet communication. The research that was done implemented aggressive electrical wire technologies. However, this also highlights the performance bottleneck of electrical networks. As these are scaled up, they become more energy intensive and less efficient, and therefore an alternative is needed. Next were wireless channels for interchiplet CNN inference. This had higher scalability compared to electrical networks, but the bandwidth for that higher scalability is very cost intensive. Next is prior photonic interconnects on chiplet-based architectures. These leverage the distance independent feature of photonics. However, the implementation cost was high due to all-to-all communication and bandwidth distribution. The bandwidth distribution was it was uniform distribution, where some areas had more bandwidth than they needed, and others did not have enough what they needed, which is one of the things Sprint aims to fix. Furthermore, conventional CNN data flow optimizations were proposed for metallic interconnects. The target was reducing data transmission distance through local data reuse. However, in Sprint and photonics, data transmission distance is not a primary obstacle. Going back to the distance independence property, implementing more efficient designs through local reuse can actually harm photonic architecture because of the distance independence property. It's a double-edged sword. Furthermore, high counts of costly electrical to optical and optical to electrical signal conversions can impact system performance, which again links back to the data transmission distance as not being a primary obstacle. So moving into the acronym of Sprint and the motivations and goals of the paper, the goal of the paper was to exploit communication patterns in CNN inference. It aimed to improve performance metrics such as execution time and energy consumption, and it also sought to reduce implementation cost. And there's the acronym at the bottom: Silicon Photonic Reconfigurable Interconnects. Next is the exploitation of CNN patterns and photonic advantages. For communication patterns, CNN accelerated communication patterns, they're fairly regular, and they're determined by the nested loop and computing system parameters in convolutional neural networks. And a dynamic network can efficiently support recurrent communications. Going back to the all-to-all issue described in previous works, some areas had more bandwidth than they needed, which was bandwidth that wasn't being used effectively, and some areas had less bandwidth than they needed, causing a bottleneck. So by having a dynamic network that can support that can reconfigure itself based off of demands, it maximizes the amount of usable bandwidth and efficiency. Moving on to the photonic interconnects, microring resonator count scales quadratically in a photonic crossbar models. Furthermore, this paper described using microring resonators being tuned by a resistive heater. Sprint is designed specifically for convolutional neural network interface. This allowed them to use fewer microring resonators, meaning fewer resistive heaters. And fewer resistive heaters is always good, because resistive heaters as a concept aren't good. There's thermal crosstalk. They constantly drain power. Among other factors, there are better alternatives out, such as physical designs meant to move things using electronically controlling a PN junction to tune microring resonators. But in short, microring resonators tuned by a resistive heater is not a good design, as not a good design. For photonic interchiplet components, Sprint utilizes electrical optical switches to combine or separate multiple waveguides. Sprint utilizes tunable splitters to operate within the transients between on and off resonance, and these two optical components are what support the dynamic communication patterns. Next is the interchiplet network. Wavelengths are allocated non-uniformly based on bandwidth demand. Again, different areas need different amounts of bandwidth. So if one area has less of a requirement and one area needs more, they can shift bandwidth to prevent bottlenecks and furthermore prevent in bandwidth that isn't being used. The number of wavelengths in a group is proportional to the count of accelerator chiplets in the system, and there are three communication modes for data transmission: unicast, broadcast, and hybrid. To start off, we have unicast. This is utilized for simultaneous transmission of exclusive data from the global buffer to each accelerator chiplet. It's grouped by equal bandwidth. The 1x2 electrical optical switches are tuned at off resonance, and the tunable splitters are disabled because no accelerator chiplets share the same communication channel. Next is broadcast mode. This transmits the shared data from the global buffer to all accelerator chiplets in the system. Electrical optical switches are tuned on resonance to make waveguides into single write multiple read, and the tunable splitters are tuned based on their positions in the channel. So a tunable splitter that's earlier would be tuned to take less of the light from the waveguide because that light still needs to have high enough intensity for later tunable splitters, whereas the tunable splitter at the end, it doesn't really matter. So it doesn't matter as much, so it's not tuned. It has more options. Next is hybrid mode. This is multiple single write multiple read channels are derived from the waveguides. Electrical optical switches are tuned to separate these segmented channels, and the tunable splitters are adjusted based on their positions in the segmented channel, as mentioned prior. This is specifically designed to support sophisticated communication. Furthermore, the electrical optical switches are tuned to separate channels to maintain intra-segment connectivity. Next are the chiplets themselves in Sprint. Starting with the accelerators and distance independence property, partial sums are generated in the accelerator chiplets and are transmitted to the near data accumulation engine. This significantly reduces the costly electrical-optical and optical-electrical signal conversion. Next is for accelerator chiplets use reconfiguration controller units to tune switches and splitters based on the communication mode. Next is the physical implementation, as you can see with the diagram on the right. All optical components are integrated on the photonic interposer. Drop ports of tunable splitters are connected to photodetectors through separate layers to avoid waveguide crossing. Next is the dynamic data flow property. So starting with package level partitions, through spatial distribution of weight kernels and temporal iterations of computations, this leads to more opportunities for broadcasting and multicasting communication, which is good. The number of costly signal conversions is reduced as accumulation computations are confined within individual accelerator chips, which is good because this reduces the electrical, optical, and optical to electrical signal conversions that are really costly in photonics. Next is the weight stationary data flow. Global buffer to accelerator communication switches regularly based on transmission data. The weights from the same input channel but different weight kernel are distributed to different accelerator chiplets through the unicast mode. Output features are calculated by accumulating partial sums, and sufficient buffer capacity for input data and intermediate results can reduce the times switching communication mode is needed. Furthermore, the weights are, as previously mentioned, are distributed through unicast, and the weight stationary data flow keeps weights stationary within the processing element, so no other weights need to be transmitted before the loop iteration ends. Next, chip iteration and underlying data flow has significant impact on communication from global buffer to accelerators. Weight stationary is really good because it utilizes different properties such as the distance independence property and other advantages of photonics and Sprint. Whereas we'll see with row stationary data flow, because it's focused so heavily on local reuse, it has trouble, and Sprint and photonics have trouble really separating efficiency wise, because they aren't row stationary isn't designed to support those very well. Next is the evaluation and simulation itself. The simulators used were open source time loop. This was used to support the non-uniform latency and bandwidth distribution between the processing elements. Execution time was derived from computation and communication time. The number of calculations and accesses to on-package memory were recorded. These were also used in calculations. The delay for electrical optical switches and splitters was set to 500 picoseconds, and off-package communication was acquired through DRAM Sim 2. Next is the power consumption simulation. Synopsys Design Compiler was used for the power consumption on accelerators and near data accumulation engines, while memory hierarchies and off-package DRAM was obtained through Cacti 6.0 and DRAM Sim 2 respectively. Next are the two equations for figuring out the energy power consumption of photonic interconnects. First is P laser, the power of the laser assembly. This breaks up into three parts, as we'll see on the next slide. But PTX is the power consumption of the transmission circuitry. PRX is the power consumption of the receiving circuitry, and both transmission and receiving factored in the heaters within the microwave micro-ring resonators in the calculations. Next is the laser equation. PRS represents the photoconductor sensitivity. C loss represents the insertion loss from different circuit parameters, while M system is the system margin, which was assumed to be 4 decibels based off of previous research. Next are the comparisons. Sprint architecture is compared with an electrical mesh and a photonic crossbar architectures. Both of these were state of the art. The maximum number of accelerator chiplets in broadcast is set to 16 for Sprint. Furthermore, this was specifically to keep the maximum number of accelerator chiplets limited to keep the laser power within reasonable range. And while photonic crossbar was originally designed to connect CPU and GPU chiplets, accelerator chiplets replaced both of these to allow for a fair comparison. Next were the benchmarks that were used. There were 4 CNN models, convolutional neural network models that were chosen. VGG16 and ResNet 50. They were evaluated in a layer-by-layer format in order to They were evaluated in a layer-by-layer format in order to get a clearer comparison of what was happening with each layer. However, compared to DenseNet and DenseNet 201 and EfficiNet V7, only their results were evaluated because they were so dense. Furthermore, redundant layers with the same configuration parameters were removed. Next were the results of the simulation. On screen now is the execution time for wait stationary. It's kind of hard to see. The graph is in grayscale, but as you can see, Sprint has the lowest execution time in wait stationary data flows. Moving on, against the electrical mesh architecture, Sprint had a 27 to 76% execution time reduction in VGG16, and it was faster. It was 28 to 66% faster in ResNet 50. Against the photonic crossbar, Sprint displayed a 8% to 58% speed up in VGG16 and a 1% to 50% speed up in ResNet 50. Sprint performed well against the electric mesh as data was frequently moved along the memory hierarchy. This proved to be efficient because for photonics, all you have to do is generate the initial photon, and that photon is self-sustaining until it is absorbed, where as compared to electronic meshes where you need to constantly supply voltages, constantly supply current, constantly draw in power. Furthermore, Sprint outperforms the electronic crossbar thanks to its real bandwidth demand compared to the equal distribution in the photonic crossbar. Next is row stationary. As you can see, again, Sprint had the lowest execution time. However, it's less than with wait stationary, because as previously mentioned, row stationary was optimized for local data reuse, and what that means is that with With photonics distance independence, the two don't mesh very well. So as a result, even though Sprint was able to make row stationary more efficient, it's not ideal for photonics in general. In comparison to the electrical mesh architecture, Sprint featured a 28 to 63% reduction in execution time for VGG16. It boasted a 24% to 61% speedup for ResNet 50. And compared to the photonic crossbar architecture, Sprint had a 14% to 39% speedup in VGG16, and it outpaced the photonic crossbar by 11% to 25% in ResNet 50. The execution time reduction is reduced compared to the electrical mesh as the partial sums were constantly streamed out of their accelerator chiplets. This led to more inter-chiplet communication, which led to more bottlenecks. Again, row stationary and photonics did not mesh well within this paper. Next is the energy consumption. Over on the left is the energy consumption graphs for ResNet 50 and EfficientNet. As you can see, Sprint has the lowest energy consumption out of all of them. And over on the right is the energy consumption breakdown for weight stationary and row stationary. As you can, it's a little hard to see because it's in grayscale, but as you can see, the ring heating does play a significant portion within tuning, especially within row stationary, where I'm under the assumption that they had to tune the resonators more because they had to constantly update the weights, and in order to update the weights, you have to send out those weights, and the different resonators need to be tuned to receive the correct weights. So as a result, this increased the ring heating. But the point that I'm trying to make is that a large portion of the pie charts are taken up by ring heating, and ring heating in and of itself is not efficient. For energy consumption, in contrast to the electrical mesh, Sprint achieved a 19 to 68% reduction in VGG16, and it achieved a 32% to 72% reduction in ResNet 50. Against the electrical mesh, the majority of the savings come from the energy-saving inter-chiplet communications. Again, for photonics, all you need to do is generate the photon, and it will sustain itself until absorbed. Where for electrical signaling, you need to constantly supply voltage, constantly supply current. You're constantly draining power to send a signal. Compared to the photonic crossbar, Sprint achieved a 9 to 52% reduction in energy consumption in VGG16, and it had a 22% to 69% reduction in ResNet 50. For the photonic crossbar, the savings mainly come from the reduction of micro-ring resonators, as saw in the previous pie chart. Micro-ring resonators take up the heaters for the micro-ring resonators took up a large portion of the energy consumption graph, so reducing the amount of micro-ring resonators, especially those that use heating for tuning, will greatly improve efficiency. Next is the adaptability. Sprint is the most advantageous when no local reuse chiplets are used. The large amount of inter-chiplet data transmission fully exploits the photonic inter-chiplet network, and Sprint is least advantageous when row stationary chiplets are used. The enhanced network data reuse makes the impact of an The enhanced data reuse makes the impact of an advanced inter-chiplet network less significant. Again, with row stationary distance independence, it doesn't matter how far away it is because it's distance independent, but something that's designed for local reuse and something that was designed for local reuse at the cost of that distance independence leads to the two of them not meshing well. Next is the scalability. Photonic crossbar and Sprint perform worse when the number of chiplets are low. This is due to a lot of expensive optical to electrical and electrical to optical signal conversions. Photonic crossbar and Sprint display good scalability thanks to their distance independence property. Sprint energy consumption scales best due to photonics and linear growth of micro-ring resonators as opposed to the quadratic growth within photonic crossbar. And Sprint has better performance as the number of processing elements per accelerator chiplet increases. This concludes the Project 3 presentation for EE599. Thank you for your time.